Yeah, so welcome. We are going to talk a little bit about rule-based languages, which you might not know what it is, which is good, because that's what we're going to talk about. And the sort of subject of the lecture is an obsession with modularity. You can see that we said from modular design to modular verification, so modules everywhere. So there has been before classes at OPLSS on rule-based languages. And if you look at, I think, 2014, Arvin gave a lecture on rule-based languages, of which the canonical example is the language named BlueSpec. So, you know, we were looking at how are we going to present it this time. A lot of things happened since then. Now we are shifting more and more to start from the ground up with modules. So after a short introduction to a bit of motivation of what we mean by hardware language and why we think it's an interesting subject, I will directly go a little bit today into math, which is the underlying, a little bit like Alexandra talked about automata and formalize the notion of automata. I'm going to formalize a sort of similar notion of computation, which is not going to be finite automata, but going to be a form of abstract state machine. And that's going to be sort of the mathematical ground on which we're going to stand and do most of our work. So first lecture will be mostly theory. Second lecture will be basically, hey, let's actually do things with that. So we are going to program, live program, and write a little processor. And then we are going to go into proofs and show that all this formalism and all this language allow us to prove correctness of hardware design. And by correctness, we will have to define what we mean by correctness. But hopefully, we should be able to get to small examples that outline a little bit how we go about all that. You know, one of the interesting things that will be very different from the lecture we just had is that in our world, nothing is finite. There is no decision procedure. Everything is just, you know, sweat. We have to write the proof by ourselves. There is nothing to help us. So you will get a feeling for that very quickly when we go to the proof, and you have to exhibit yourself your little mathematical objects that allow you to make your proof. So why do we want to do hardware language, design programming language for hardware? So for a long time, I think until quite recently, people thought that there was basically two companies designing hardware, you know, AMD and Intel. And well, before that there were more, but like for 20 years there was only them. But now it seems that every company and the neighbors are doing hardware, specialized hardware like everywhere. And you might know already, but the challenge with hardware is not necessarily to design it, but it's to test it and to make sure that it actually does what you want it to do, which already knowing what you want it to do is already unclear. So for us, really the challenge is specification of what the machine should do, and then design, and then verification that the machine does what it should do. And obviously, the main difference with standard programming language is the fact that the execution model of hardware is fundamentally parallel. You know, there's a lot of concurrency happening. So we will very quickly, you know, get hit by the wall of concurrency, and we will have to do things about it. Okay, so, you know, I want to start with a little bit of definitions and math and examples, a billion examples, because I know how to do examples. And it's easy. So I start with a module, because I said twice modular, so I need to talk about modules somewhere. So let's define what's a module. And it's going to be a bit like an automata, but a bit different. So it also have a set of states which have some type, but it's not necessarily finite. So this is an arbitrary type. Then it will have what we will call a collection of rules that I'm going to explain in a sec what it is, which is finite. Then it's going to have a collection of action method, which is going to be finite. And then it's going to have a collection of value method, which is also going to be finite. And I'm going to put it here. Okay, and now I want to tell you right now what are all those things. So the thing that is very similar to automata are, in a sense, the states, and all those are transitions of the machine. So let me give you a first example of the type of those objects, what they correspond to, and a typical example of those things. So a role is going to be a relation between states. So it's just going to be S, a subset of S cross S. Okay, and it's just very similar to transition in an automata. when you have a state, what are all the possible next states that you can go to? Except that rules, the transitions are not labeled. They are epsilon transitions. They just spontaneously occur, like in automata, you have epsilon transitions. Okay? Then action methods are going to be a subset of S cross an argument that you feed it. And let's say for the sake of the first lecture, we're going to consider that all our methods only have one argument, which is a natural number. You know, if we can handle one argument, we can probably handle two arguments and then as many arguments as we want. And we don't need to care too much about types yet. So let's just say that we have one argument always, and it's always of type natural number. And an action method is basically a relation which say, if I were in some states and I were to call the machine with some arguments, then I will end up in some new states. Okay? And there might be more than one new state because it's a relation, and there may be 0 new states, which is the relation is partial. Okay? And value methods are the only way to observe anything in the system. They are the observation function. And let's say that the observation are always going to be of type nat for now. So here, the observation is if I had a state and I try to call the value method on that state with some argument, then I will observe some return value. And maybe I will observe nothing because I cannot observe anything currently, and then it's a partial relation. Or maybe there is more than one possible thing I can observe. Okay? So let me give you a first example. Let's actually give, I think she gave the example in the first lecture of the simplest system that is interesting. Let's call it the coffee tea machine. This is actually an example due to Robin Milner, I heard. Nate Foster told me that. And so in this example, the states, we are going to have that many states, 1, 2, 3. So note first that I had the number of value method and the number of action method and the number of rules were indexed by a finite family. And I can think of the number of action method and the number of value method as the signature of a machine. For example, if I have one action method, and that action method is labeled by something called, let's say, put money in it, then it means that I can do the action put money in it, and the machine has a transition put money. So I have this transition here. I could have a put money. If I am in that state and I call the put money thing action method, I can end up in that state. Then if I'm in that state, I can either choose between get coffee and get tea, which is 2 action method, and I end up in that state. And then I can have a value method, which is an observation, which is going to be not defined on any of those states, but on this state, the value method is going to basically return, let's call that method the C method. And it's going to return, in this case, coffee, and in this case, tea. And you're going to say, well, how can you do that? You don't have enumeration type. I can encode enumeration in natural numbers, and everything is fine. Okay? And if I wanted to look at this machine and write explicitly the transition, it's very easy. There is no rules. There is no epsilon transition, no spontaneous transitions. So if I write my state machine, the set of state is going to be just the set 1, 2, 3, 4. Then the rules is going to be the empty set of rules. That is, curly R is nothing. Then the action method, I'm going to reverse action and value. The action method are going to be put money, get tea, and get coffee. And I can describe them simply by saying, well, I need 3 things. I need get tea, which is a subset of previous arguments next. And here I just ignore my argument. So get t is going to be equal to the set of, there's only one thing in which I can do get t. It's when I'm in state 2. And then for anything, and then I get into state 4. Okay? And I could describe get coffee as well, which would go from 2 to 3. And then I could describe put money. And let's say that in this case, I just want to accept a fixed amount of money, for example, 1. Otherwise, I just don't accept to put any money. And then it would be 1, 1, 2. OK? Then I describe the final transition of the system, which is the observation mechanism. And here I could just define there is only one of them, C, which is just a set. And I can see in 2 different states. If I am in state 3, I see coffee. And if I am in state 4, I see tea. OK? Any question? It's fairly straightforward. I'm just describing a sort of set theoretic way to describe things that look like an automata. And I can just, go and unfold the definition and everything is good. OK? Yes? Oh, I put star, which is basically the set of all the triples such that the middle one is an arbitrary number in this instantiation. OK. OK, so here I really didn't do any programming, right? I'm describing a mathematical object that is a transition system. And that transition system has a few similarities with automaton and a few dissimilarities with automaton. The similarity is that in this specific example, there is a finite number of states. And, that's sort of an accident. I could have picked an infinite number of states. And then I have sort of sliced my transitions between things that are about changing the state of the system and things that are observing the state of the system and things that are spontaneous transition of the system. OK? Very good. So now, actually, this system is not, it's good to just make sure that we understand the types of, the structure of the machine. But the things that we want to, we will be interested in is basically we'll be interested in modeling the basic blocks of hardware, registers, memory, and stuff like this, as this kind of machinery, as this kind of object. And then once we will have that, we will write a language to plug together such modules, to make bigger modules. And our language will be such that if the leaves of our systems are synthesizable, if they are hardware representable, then every time we compose, we keep being hardware representable. And so the way we are going to build hardware will be by starting from a set of primitive modules, which are going to be such objects. And then we are going to just design the language to compose those things together. Okay? And there will be sort of plot twist on this language. Now, I want to give you more interesting or slightly different examples, which are very easy but very useful. Another example would be a register. And what would be a register? Well, let's say it would be a register that just holds one value. And it doesn't have neither any internal rules. Actually, for a little bit, even though it's rule-based language, there will be no rules. Then it just has one action method, which is going to be the write method. And the write method is going to be simply saying that if I were in a state x, any state x, and I were to write value y, then I could always write value y, and I will always end up in state y. Does that make sense? The fact that this is a register, it's basically something that if I call the write method to it. Oh yeah, something interesting that I didn't say. So sometimes I like to call modules abstract state machine. And the reason why I like to call them abstract state machine is because they look a little bit like abstract data types. And abstract data types are types that you can only access through their interface. And here, that's basically the philosophy. You can only you never can really look at the internal state of the machine. You can only access it through its method. OK? State machine. So here I am describing a register. And a register is basically something that has a relation on old state, new state, where I can write to it. And then the new state is the value that I wrote. And there is also an observation method, which is the read value. And the read value, again, ignoring its argument. So if I were in state x, I were to call with an arbitrary, I need to be careful with star and x, no. Then I will necessarily return x. OK, so I could actually write it like this to avoid. Let's be precise. X. Is that sort of convincing that this corresponds to a read? Yes. Yes. Oh no, I said they don't have to be. No, sorry. Okay, they don't have to be finite, but the number of them have to be finite. That is, here there is one, here there is one, but each of them is infinite.
The number of relations has to be finite, but the relations themselves can be.
Correct. Thank you. Yes, there was another question. Was it the problem?
That was my question.
Okay, thank you. Okay.
I also have a question.
Yes.
When you say abstract state machine,
Yes.
do you mean the currently
No.
abstract
No,
machine?
that's why I didn't name it like this, because, so that's a good point. The reason why I didn't name it abstract state machine is because there exists already an object in computer science called abstract state machine that have sort of something to do with that, but it's not the same definition. So this is sort of an illegal secret name for this because the name was already taken. But it's kind of a good name because it really sort of gives a vibe that you access it only through its interface, like an ADT, okay? Okay, so I gave you an example for a register. And now I want to give you an example, which is going to be sort of more infinite. There is nothing that prevents you to... oh, I can use the third one. Yeah. So I can give you a sort of thing that has no chance. So this has a good taste that actually we can build hardware that does that, not for natural number, because natural number is infinite, but if you were to replace this with a bit vector 32, then you could actually build such machines that just store a value, and then you can read and write. But no, let me give you an example, if I can hold that little one down, where you will never be able to represent it in hardware, but it will still be useful. And that's an important thing of this reasoning framework that we're describing, our programming model, is the fact that we can talk about objects that we can't build, but it's useful to introduce them a little bit like imaginary number, complex numbers in math, where you introduce something that help you solve problems. And for a little bit, you have things that are not synthesizable, and then you're going to erase them, and you're going to come back to the nice world of synthesizability. Okay, so, but that is going to become clear later. So an example is infinite memory. Infinite atomic memory, let's call it. And in this case, the state is slightly more interesting. The state is going to become a function from n to n. And then we are going to have still no rules, because we do rule-based languages. And then we are going to have a read method, but here the read, conceptually, the argument corresponds to an address. Okay? And now the semantics of the read is going to be the following. It's going to be, sorry, so that's a value method. I need to be a little bit careful with where I put the value and what I put the actions. So the read is going to be defined by if I am in some state X, let's call it actually F, and then I have some queries that I want to make to the memory, then I should return F of arg. For F arg. And that's all. Okay? And I could do a similar thing for write, where I could say, well, if I had an old state, maybe I should do it actually, instead of saying that I can do it. If I had a function f, and then I wanted to update with a pair of arguments of index and value, then I would produce a new f prime. And this relation should only hold if for all index such that either index, for all j, otherwise I have shadowing, index is different from j, then f prime of j equal f of j. And then if f of f prime of index equal v. Does it make sense that this corresponds to an infinite memory? Can you, yes?
I was wondering why you wanted the finite number of relations, because it seems like you can encode an infinite number using one single relation.
Yes. The reason why we want that is because, so as I said, the first part is basically math. And as you are saying, because it's basically math, you can encode basically a lot of things. But then at some point, we are going to fork off and do hardware. And then we are going to have to add a whole bunch of restrictions to make sure that all those things are synthesizable and that they make sense in terms of hardware. But no, we could get away with that. But for later, it will make more sense. Yes, I didn't realize that this could be a problem. Could trip you off. Is it good? OK, and you need to remember that because the thing goes on its own. Git erase. Oh, maybe I can hack something. No, I can't hack something. OK. OK, so, oh, I need to go faster. So this is, I'm not going to do an example in which I would write, well, I think you can do it. It's fairly trivial. I can do, when you start saying it's very trivial, usually that means there's a scam. You could do a queue in which, oh, that's an exercise. So the state would be a list of natural number. And then you still would have no rules. And then you would have one action method that would be to be able to enqueue something, one to be able to dequeue something, and then you will just have one observation that would be the first, right? And I think it would not be very hard for most of you to be, or for all of you, to be able to write those relations mathematically, OK? OK, very good. So now we can get down to the last sort of like mathematical blah blah before we can get to programming. So one question that we often ask ourselves when we are doing programming language, and we already asked that question several times, is when are two programs similar, or how to compare the semantics of programs. And here it is especially useful because you see me coming, right? I'm going to tell you at some point, hey, I have two modules. They have completely different S. They have completely different set of rules. They have different body for the definition of the method, but somehow they are equivalent. One is an implementation, one is a specification, and we would like to be able to formalize this notion of equivalence, where one might be a very high-level mathematical model, which is something that I can't synthesize, and one might be something completely synthesizable. And then I'm happy to know that, in some sense, that they are equivalent. So now we need to define what is the notion of equivalent. And we are lucky because we have choices. Well, I'm not sure if we are lucky, but there's more than one way to define equivalence. And they are interesting. So I'm going to describe two ways in which we can describe that machines are equivalent. And I'm going to let you pick which one you prefer. Equivalence. Actually, we are not going to do equivalence because equivalence is usually too strong. So what we are going to do is going to be called refinement. Let's call it refinement. And the idea will be that if you refine each other in both directions, then you are equivalent. So if we can define the notion of refinement, then we can define the notion of refinement of equivalence. But in most situations, we won't care about equivalence. We only care about one side of the ordering. OK, so what would be a way in which we could define the notion of equivalence? So if you remember what Alexandra did, in the case of automata, it was basically you construct the language that is generated by the automata. Or you construct a language which is accepted by the automata, which you can sort of think of it as a trace of all the possible behaviors that are outputted by the automata, right? It's like, you had paths, and yet you're looking at all the possible paths, and you're generating a trace for them, OK? So that's one way to define it. And we can basically define a notion of trace for definition. And it's slightly more painful than for automata, but it's still doable. We can define the traces of a module or the behaviors of a module the following way. So you will need to have an initial state or a set of initial state, but let's go with one initial state because it's less painful, S0. And then what we are going to say is, well, there is only a few things that you can do. You can either do a silent transition, which is pick a rule, and go to some new state S1. And when you do that, you do not create anything in the trace because it's a silent transition. If you take a step, which is an action method, for some argument, then you basically are going to record it in the trace, where you're going to say, if I had trace L here, so I start with trace empty, then after I add that, I end up in a trace where I just have recordings that I am, let's put a concrete number here, an action method. And then, I can just inductively define, every time I have an action method, I can inductively define a trace of action method calls that I could do, okay? Except that in my trace, I should also want to inject the observation that one might do. And here I don't have any observation. I just have transitions of my system. But that's not too painful because I can just hack my definition and say, well, if I go anywhere else, I'm actually taking a little bit of time to also interject any observations that I could make at this point in time. So now I can say, as an example, S0, let's say that I have an epsilon transition, which is one of the rules. Let's say that I have an enq method. So now I have a state in which I just did enq method. And then let's say that just after that, I actually want to do an observation. And so now I'm saying I can do observation without changing the state. So I stay from S to S, but I append the observation. So this is a different kind of arrow. And let's say that this observation here was for the first method. And so in this case, my trace is going to be extended by the following. I did first, and I put an arrow to say, and I observed 1. Okay? Question?
More formally, would you have to supply an argument first?
Yes. So that depends on how you encode the language in your proof assistant. If you're talking about the real implementation. Yeah, so if you take at the formalisms that I gave just before, then you would basically never have just one trace. You would have all of them because I could put first 1, first 2, first 3, first 4. You would have an infinite set of traces that would correspond to that thing. Yes?
Infinite traces? Yes, no?
Do we want to do co-induction, really? The answer is, so the question is infinite traces, yes, no, opinions, maybe. And I think you can. So, but the problem is that then all your proofs are co-inductive proof, and then you are unhappy. Or it's harder. So we are gonna stay with only finite traces. Yes?
Do you pick any ordering of the
Sorry?
ordering for the observations?
Very excellent question. No, it doesn't matter necessarily because if you do 6 observations in a row, but you don't have any action method because you didn't change the state, then you have sort of you can prove that whenever you have 2 observations back to back, you also necessarily have the trace in which you can permute the 2 observations and observe the same thing. Okay? Okay. Silent rule here, what I meant by epsilon is anything in R. Okay? Okay, very good. So now we have a notion of trace, and we are so tempted to define a notion of refinement by saying that, and we will say it, that a system A refines a system B if and only if, you can probably guess the definition. So because I don't have time, I don't do that formally, and then this can be done formally, and it can define, let's say, semantics of M as a set of all the traces. And now we will say a module M, so definition of refinement. I need to learn how to erase a bone. Module M refines a module M prime is defined by, I look at the set of all the traces and I compare it to the set of all the traces of M prime. Okay? And that's a fairly simple definition. Yes?
Do we require this case that the set of methods inside?
Well, so it's impossible that this property is true, except if there's a subset of them. So no, they don't have to. So, okay, philosophy. Do you want subtyping in your language, or do you not want subtyping? So the first thing is if they have disjoint set of methods, there is no chance that this property is ever going to be true, because except if those are fake methods that can never be called, there will always be a trace that contains that method inside the trace. And this one that is in the implementation won't be on the specification, so it will contradict that property. You see what I'm trying to say?
Yeah, I think my question was
Do you want to be able to allow renaming of things? No, let's assume that we just have the same set of methods, and we are only interested in showing refinement when the methods map one-to-one, and that we don't have to worry about this kind of thing, okay? But sometimes it's kind of interesting to think about subtyping of re-injecting, but let's not do that, yeah.
So there's no like temporal ordering from the traces?
What do you mean by temporal ordering here?
So you have the set of traces. Like
Yes, so
first, ink to be the like the first one, and the first to be the second.
no, yeah, so it's a set. So it's a set, so it's describing a set, and there is no ordering between the elements in that set.
Well, the question was about the actual elements, the individual elements of the trace. This is an ordered sequence.
Well, so the element of the trace is an ordered sequence, but between traces, those are not ordered. Yes?
Is equality between traces just like
Yes. Okay, but look at all those traces. They are infinite objects, right? So that's why here we are just doing math. We are not doing programming yet. Okay. Okay. So very good. And why is that a bad definition? Well, I mean it's a good definition, but then sometimes it creates surprising machines. So I told you about the tea or coffee machines, and now I want to tell you about the tea of coffee machine, which is an implementation. So I forgot, did I give a name to that machine? I think it was the tea coffee machine. And now I want to define TC prime. And TC prime is another tea coffee machine, but it's as follow. It's like you give money, put money, but it's non-deterministic to either of those states. And then in that state, you can only do get coffee. And in that state, you can only do get tea. And so here, you can observe that you have tea. Here, you can observe you have coffee. But it's different because the choice of is it tea or coffee is not made by you, but it's made by the internals of the machine of did I go left or did I go right when I decided to, when I called the put machine. Okay? So now, TC prime refines TC because it's the case that if I look at all the traces of TC prime, basically TC prime have just put money, get coffee, put money, get tea, and then observe. But there is no trace that allow me to distinguish TC prime from TC, which is quite a shame because I don't like that machine, because I can't choose if I want coffee or tea. Okay? And that's the example that is coming from Milner. It was a typical example of, oh, it's a very natural definition, it's very good. But the problem is that the choice, the moment that the choice is resolved, is not mapping one-to-one, and then you end up in that situation where sometimes you might not want to say that those machines are equivalent. Yes? So the put method, the put money, was a relation. So there could be more than one successor state. And here there would be two successor states. There would be either the state 2 or the state 3. And which one it goes to is non-deterministic inside the language, inside the box, instead of being used at chooses. Okay? Okay. So this is good, and we're actually going to be interested in proving property for that. You can actually feel like one way to sort of say this is an okay definition is to say it could be a sort of a, if you look at it as a black box and there is just two buttons and one thing to put money, and you think of this notion of partiality as I can't yet push the button, then you could think of it like maybe that machine it's just a problem of liveness. It's like if I were to wait longer, maybe at some point it would allow me to get a coffee, but it still has not allowed me to get a coffee. And I know if I were to open the box of the machine that it will never allow me to get a coffee. But if I look at it from the perspective of the interface, maybe it's just that there are internal transitions that in 6 billion years, I will be able to get my coffee. Okay? So and that's, I think I said a few words at the beginning where we are going to be interested mostly in functional correctness and not liveness. But there are many situations in which sort of intuition is coming from liveness things. And so definition, when you just look at it from a purely functional correctness, are actually still sound. Okay? But anyway, there is another definition, which is the one that I'm mostly interested in, which is stronger. We like both, but stronger. And it's a notion of simulation, and more precisely of weak simulation, which, if you listen carefully, the word was said in the previous lecture. It was said in the context of bisimulation. or B simulation, I'm not sure. And this is a sort of stronger definition because it's going to require that the machine stays in lockstep, and that really for any reachable state, there is a state corresponding in your other machine such that they keep being indistinguishable. So definition of weak simulation. And very easy. It says, so we say that a module M and a module M prime are such that phi is witnessing that M prime simulates M if and only if the following. So M prime, so phi witness that M prime simulates M if and only if the initial state, when they're in the initial state, so if I look at, let's say, small m0 and small m prime 0, oh, I need to tell you what is phi. So phi is a relation between the state of m and the state of m prime. Okay? And it must be the case that phi of m0, sorry. So, okay, let me tell you one thing about notation right now. So we can write this if we want to view the world as a set theory world. But very quickly, we're going to shift to a programming view of the world. And when we look at it from a programming view of the world, we will write this, m0, m prime 0. And why is that sort of equivalent? Because you're going to think of phi as a function which takes a pair of states and return a Boolean, but not quite a Boolean because you want to be able to do math, and it's a proposition. But yeah, let's not get too much into that. This is for proof assistant people. So sometimes I'm going to use that notation, but you can think of it like this. You can desugar it to that, okay? Yes?
So we're requiring now that modules also have a determined starting state. It's now part of the
Yeah, so to make it less painful for me to sort of add all the conditions, yes, but all this work for an arbitrary predicate. Okay? Okay, so it has to be the case that at the beginning of the world, they map, okay, and that the observation map. So that's sort of the observation, which is that for all observation functions inside the, I think I called it V, value method, for all arguments I could call to the observation, feed to the observation, it must be the case that if I do V, and I use the notation of application, where I apply it to the state M0, and then arg, then this must be in the relation. So let me write it as a relation, it will be cleaner. Otherwise, it will be, I need to stand on, where can I get? Okay, yeah. Okay, so for all value method side V, for all arguments, must be the case that if I have a triple M0 argument return value inside V, so this is, it must be the case that it's also inside this specification. Okay? So I'm just saying, if I were to be able to observe in my initial state some value by feeding some arguments, then I could observe the same value rats if I were to feed the same argument to the specification. It's plausible deniability. It's like you don't know if it's a spec or the implementation, because both of them could have returned that value. Okay? Does it make sense? Yes?
About phi.
Yes?
Do we necessarily, or should we necessarily assume the obvious about it, like transitivity?
So what do you mean by no? So you're saying that is it the case that I can prove a theorem that phi is necessarily transitive once I will have finished my definition? Is it your question? Sorry?
I thought you finished your definition.
No, I just did the base case. I need to tell you that it kept being inductive, because right now I just tell you that they are indistinguishable at the beginning of the world. But then there's going to be something happening, that is the system is going to evolve, and it's to keep the case that it keeps, okay? But so you see it coming, right? I'm going to do an inductive case. So this was the base case. And in the inductive case, it's basically going to say the following. For all states, M prime, where M was in the state of M was in the state of M prime, such that the pair M and M prime is in the relation. Okay? It must be the case that if I were able to call an action method on one side, action method on one side of the implementation, so A of the implementation, for all arg, must be the case that if I were to go from M, I call, let M2, I call action method with arg. Must be the case that I can also call it on M prime. Okay, that is, if I can take a step on my implementation, calling some action method, I should also be able to call a step on my specification, and it should be the case that my two new states are still in the relation, that they are still related, and that's the whole part about being inductive, that they are such that n phi of M2, M prime 2. Okay? Yes? It exists existentially quantified. Yes, I didn't put it. Very good point. So for all new states of the implementation, there must exist a state in the specification such that these steps. Okay? So it's saying that if I can take a step on the implementation, it brings me somewhere. There must be a place to go in the specification that also I can call the same action method from that state. Yes?
So you can multi-step on the right side, so you'd be losing information possibly.
So what do you mean by multi-stepping? Here,
I'm just so like if this only takes one step on the left side, the right side might take several steps, but it'll get to a state where they match finally. Is that the idea?
So here, my definition is not yet exactly complete, and you're bringing something that I wanted to discuss exactly, and maybe you're reacting to the fact that I said weak, and it's not weak here. So right now, I'm basically saying that there is a strong simulation, because if I take one step on the left-hand side, I must be able to take one step exactly on the right-hand side. That's called a strong simulation, but it's too strong because it's named strong. So instead, we want a weak simulation. And a weak simulation, we say, actually, you know what? My right-hand side is allowed to take a few of those R steps, those silent steps. So instead of just saying I go to M2 prime, I say I go to M2 prime, and then I get a little bit of freedom, a little bit of slack to do any non-deterministic steps in R, okay? And so, oh, I can't put it up, so I have to, I don't know. So instead of being directly, I require that I am directly related after M2 prime, I'm actually saying there exists an M2 prime second, which is further than M2 prime, such that I go from M2 prime to M2 prime second with internal rules of the system M prime. Okay, this is complicated, so I have a diagram that summarizes the whole thing very quickly. And it's much cleaner than these formulas, but these formulas are unambiguous when the diagram is sort of ambiguous. So the diagram looks like this. We are going to draw, if I have my state M here, I have my state M prime here, and that they are related by phi. If I take a step of with an action method, calling argument arg, I get to some new state, M prime, then there must exist first I can call AM on R, and then maybe I want to take a few steps of internal transitions such that my new state, M prime 2, are related. Well, billion questions.
Do you have two M primes? Should that bottom left M prime be an M2?
Yes, I have, yeah. Okay, so let's use a new convention. We're going to say that when we name the top left, we name it north-west, north-east, south-east, south-west. Okay? Yes?
Does it have to be in that order, or can you take silent steps, get to the second and then the third, or is it always this ordering?
So we picked here that you take the step and then you have silent. You can actually add transition in the beginning if you want. It just happens to be enough to justify it like this.
Okay.
So, sorry, this basic question, but like,
No.
you take, so are we also allowed to take multiple steps on either side? Like right now we're taking
multiple step on the spec side, yes, but not on the implementation side. But you will see that it doesn't matter because the definition is inductive. Then you will still be able to take multiple step on the implementation side, but in the induction, right? If that makes sense.
We require the observations mentioned in the first stage. So we require the observations mentioned in the first stage.
Yeah, what you're telling me is that why is it the case that I didn't finish my definition? Yeah, that's good. You're absolutely right. That's a good point. Like, well, that's all good, but no phi, I'm not indistinguishable anymore. So I need to add the fact that it implies that they are also indistinguishable. The two new states. Okay. So there's actually a slightly better way to do it. The slightly better way is to say I'm removing the requirement for indistinguishability inside my initial case. I'm writing everything without notion of requirement of indistinguishability, and then at the end, I say, and by the way, phi implies indistinguishability. If phi I prime, then I indistinguishable from I prime. Okay? Okay. So plus indistinguishability. Okay, and I have still one case that I need to tell you. And what is the case missing? Yes? No. So termination would be liveness, in a sense. Yeah. Sorry?
Like no steps can be taken?
No steps can be taken. It would be a little bit like termination, right? It would be a liveness property. No, but there is a, yes? Exactly. There's no way to do a silent transition on the left, on the implementation side. So the case that is missing is a little bit the same, except that on this side, I'm going to do, if I were in a state, M northwest, and it was related to a state M northeast, and then I were able to take an internal transition for some rules that would bring me to M southwest, then there must exist a sequence of rules. Notice that the rules don't have the same sets on both sides, right? They are indexed by different sets. The only ones that are the same ones, the interface are the action method, but the rules are completely different. And then I would end up in M southeast. Okay? So I think at some levels, this might be a little bit confusing in definitions, but if you try to rewrite it and find it by yourself, it's sort of, that's the only thing you can do. It's like, if you are related and indistinguishable, what is the things that are needed to keep being indistinguishable when you push moving forward? Okay? Okay, so now we have defined a new notion, and the new notion is M refine M prime. Sorry, with a square things, witnessed by phi. And we have possibly a question of like, is it stronger, weaker than the previous definition of equivalence that was about traces? And it turned out that it's a very simple theorem to prove that if you have a phi witnessing a relation, then necessarily the set of traces generated by M is a subset of the set of traces generated by M prime. How would I prove that? I mean, it's always the same answer. We are in programming language class, so it's approved by. Excellent. Okay. Okay, so that's the end of the mathematics suffering. We built basically the basic tools. to be able to define the semantics of our objects, even though those objects right now are mathematical objects, they're not programming objects. So now what I want to explain a little is when you have a bunch of modules, M1, M2, M3, you would like to some sort of compose them together and build a bigger module which would do things with them. So let me give you a typical example. Let's say, I have a choice. Hard. Okay, I take my second favorite example. So I want to define a new module which would have an enqueue method, a dequeue method, except that I don't want to define it directly as a set, because that's sort of the mathematical way, but I would like to compose it from a bunch of submodules. Maybe one submodule is a queue, which is a primitive module, and then I would like to say, well, you know, this thing should just push into that queue, and it should just compose an F with it and push into that queue, and this thing should just basically pull from that queue and post-compose with G. And I would like to be able to do that where I have this system, which is a compound system, where I don't have to write explicitly all the relations. The relations are just derived from code, which would just be the glue code explaining this F and this G. Okay? So I'm going to give you a sort of 2 ways we can do it. And then, well, first, at some meta level, you know what's coming, right? You know, we need a language. What's going to be the language? Lambda calculus. And then we are going to realize that doesn't work. So then we are gonna need linearity, but we are not gonna do linearity. But before I do that, I want to show that this problem is very easy if you allow yourself to do a little bit more mathematics. So we already have, and we have done a lot of that, some mathematical language constructions to do those form of compositions, and this form of composition is the symbols that has been drawn the most number of times on this board in the last 4 days. And it is the line. So if I were to say, I have a bunch of submodules, M1 and M2, and they have a bunch of states, small m1 and small m2, and I would like to say, sorry, actually, let me just take one submodule, which is a submodule here. So let's call that submodule M, with its state corresponding small m. I can build a system over there by saying, I'm going to describe all the rules and all the methods as inference rule of a system. So I can say, there is the enqueue method, which is, if I were to be in a state small m, I wanted to apply the enqueue method to arguments on. I'm allowed to say that this goes to state m prime, if and only if it is the case that I can call the state m. I can prove that m argument, sorry, f of argument goes to m prime is inside the enqueue relation of the m guy. Okay? I realize now that I write it that there's a little bit of a confusing thing here, because this method is named enqueue and the internal method is also named enqueue. So let's disambiguate by name and let's consider the external enqueue. And let's consider this one is still called enqueue. So now the rule to say how do you define the external enqueue is simply that you define the relation on external enqueue inductively by saying you can only go from m to m prime if you go from m to m prime inside the submodule plus with the glue that you added, which was the f function. Okay? Yes? Sorry? Yeah, so that is just one rule. So now there is another rule. Sorry, that's one method. Then I'm going to have to tell you about this other method. And for the other method, I'm going to do G inside the other method. Okay, so if I am in some state M, and I want to dequeue, and I want to know when I can go to state M prime, then I'm going to say, well, that's sort of easy because it means that it must be the case that so I didn't tell you, by the way, an observation, which I think is what you wanted here. Here's the system. Actually, this is a good example. This system, there is no observation at the output, right? I can't know that it's f of g of something, g of f of something. So there is only action methods that I talked about. So it's kind of dangerous because I can never observe the value. So I need to add a value method, which is observing the output of the queue, okay? And if I define the DQ, then I'm just saying, well, that's easy. It must be the case that if I were in M, I were to feed 0 arguments. We always have this awkwardness with the arguments, blah, blah, blah. Then M prime is inside the relation NQ external of the submodule. Okay? So what's good with that, this example is a little bit contrived. If I were to make it slightly more interesting, in which instead of directly having DQ pulling from this queue, I could say, actually, there is one more thing, one more queue here, and we will write a first rule. And in this system, I would need to add one more inductive rule, in my case, and it would be to be able to bring a token here to here, right? Every single case so far was externally called, but now it needs to be an internal epsilon transition. Yes? Yes. Where did I write? Sorry. So it's DQ, but this is not the external one, it's the internal, actually. Okay.
We mentioned G somewhere.
No, and why did we not mention G? Yeah, so you are only going to mention G in the observation, right? Okay. So I did a skip, right? Oh, okay. We used to have this system where we stopped at G. And the only places where G would have shown up would be in the observation. So if we write the rule for the observation, it would have been like this. First would have been such that the first external would have been such that if I am in state M, and I call the first method, then I observe the value ret, if and only if I were to have a triple M star ret prime inside the first method of internal. Right, this is inside the first of internal, and it must be the case that ret prime of G of ret prime is equal. Okay? This is a scam. I'm just doing math. Okay? So I just what I want to outline is the fact that inference rules are a very natural way to describe those kind of relations. Because I need something, I just throw it in there. And then, it just adds constraint on what I want. So the same way, I can define an internal rule, and then there is a nice alignment, because now we need to add a rule for a rule, and a rule of a line of a rule, a deduction rule for a rule. This rule, let's say that you had an internal step. So internal, which is pulling from there and pushing to there, then it's going to look like this. So this is an internal transition. And I'm saying M, step to M prime internally, if it is the case that inside M, if I were to look, so notice first the one thing is that I had a system with a single piece of state inside, and then I just agitated my hand, and suddenly I had 2 pieces inside because it's a new system. So now it must be the case that my system is a pair of states, M1 and M2, and it goes to M1 prime and M2 prime. Okay? And then when can I step from a system where I have 2 queues in that state to 2 queues in that state? Well, it's easy. I am saying that I'm going to have to pull an element from that one and push it into this one. And this one will be the one where I pulled it from, and this one will be the new updated one. So what it's going to look like? It's going to be like, well, M1, I want to DQ from it. So it must be the case that if I dequeue from it, I go to M1 prime, okay? But then it must also be the case that if I were to take notes of what is the return value at first, I get a ret, okay? And then I want to enqueue, I think I named it G of ret inside M2, and so I get M2 prime. Okay? Doesn't make sense? Is it confusing you? I see thumbs up and I see confused look. So this is contradictory signaling. Yes?
So at high level, this is like a composition of either A as a one system.
Yeah, so this rule is basically simultaneously dequeuing from one system and enqueuing into the other system. Exactly, and actually the keyword atomic actions is very important because that's what rules are. They are atomic actions, okay? So if you were to look at the 2014 lectures, I think that the keyword that was always repeated was atomic actions and not rules, but they are similar, okay? Okay, very good. So does that make sense? Basically, I just said, hey, if we just do math, we can define our little composition problem. It's very easy. You just ask to call the sub-methods of the sub-things, and then you have a natural way to compose. Yes? Oh, boy. Which one? This one?
Yeah, can you just read what it says? It's a little hard.
Oh, internal. Just a little. The whole thing. Okay. Yeah. So the premises of the rule is must be the case that for the first queue in state M1, if I were to dequeue from it, I would get to a new state M1 prime. But if I were to look at the first element of that queue, it would be named ret. And then I would be able to enqueue ret into M2. Then I would name the new state of M2 M2 prime. So this requires a whole bunch of things, right? The premises here requires that the first queue is not empty, otherwise this cannot apply. This will be stuck because you cannot derive first return ret if there is nothing inside. Okay? You cannot also dequeue from it. Yes?
Just to clarify, so now we work with the internal state being the product. So the state
Yes, yeah, the state is the product because no, it's this one and this one.
Okay, and so the rules that we have written before should be also adapted to.
Yes, so exactly. The rule should be adapted to having pairs everywhere if you wanted to do it properly. And so no, it will mean that the rule enqueue is only acting on the left side and the rule dequeue is only acting on the right side. Very good point. Okay? Yes, question?
FG and H are just simply functions.
Yes. Yes, here it's a pure function. In hardware, we will call them combinatorial function. Combinational function. And I'm going to detail in a bit. Okay? Good? Okay. So now this is not the way we want to do it because it doesn't help. But philosophically, that's the way we want to do it. So the problem is that here, I could have written an arbitrary business here, and nobody could have prevented me to write this. Arbitrary math, I could have written for something. You know, it's very easy to have an infinite family checked here, and that you can't do anything in the hardware about it. So now what I'm going to say is that instead of using glue that is basically math, we can use lambda calculus as glue. And then I'm going to say, actually, you can also use a restricted version of lambda calculus as glue, and that can be translated to hardware. Okay? And I think I won't have time to finish the whole thing today, but at least give you the lambda calculus version and then give you an intuition. And tomorrow I'm going to do the compilation to hardware and then write a processor. Okay. So I said I wanted to talk about gluing with lambda calculus. Okay, so actually it's not even it's going to be exactly like Frank's language, the first one, where, you know, lambda calculus is cool, but there's abstraction, and abstraction is hard. So we're going to take lambda calculus without abstraction. So gluing and our construction is going to be, so what are the expressions we can do? We are going to say we have the if expression, then expression, else expression. Okay. Now we have the call of an action method, let's say, let's call it like m dot action method of argument. We are going to have the call of a value method of argument. And we are going to have application of a pure function. Let's say f of argument. Okay? So it's a small language that actually maybe an easier way to think about it than thinking about it. The reason why I mentioned lambda calculus is because internally in the BlueSpec compiler, it actually is represented as a lambda calculus. And if you were to ask it to dump the lambda term, you could see it. But maybe an easier way to think about it is as a small imperative language where you can just call action methods like an object-oriented language, call value method, then you can apply a pure function, and then you can do a conditional, okay? So there is a little bit of complexity in the semantics of that language. Why is there complexity? Because there is non-determinism. So whenever you call a value method, there might be more than one written value. So if you want to give semantics to that language, you need to say for all possible value return, okay? But you can technically, easily, now say, well, I have a very easy way to, when I have two submodules, to create a new module. And that would be simply to do the following. So let's write a queue. But instead of writing a queue as a primitive module, we want to write a queue made of two registers. So let's write a queue. Does it mean I'm late? No? I am late?
Yeah, it's okay.
It's okay. Okay. So now, what are my submodules? I'm going to have two submodules. The first submodule is going to be just a V called for valid. And that's sort of an M. I'm going to call it valid. And then another one which is going to be called data. And so both of those things are going to be registers. I'm going to write I have two registers, which are declarations of my thing, which is not a type of expression, sort of what is in scope in my system. And then I could write the transition relations just as expression of my little language, where I could say, well, and I did one more thing, sorry, abort.
The microphone is not working.
Sorry?
The microphone is not working.
Oh no. Well, it should be working.
Oh.
I think it's working.
Might have run out of butter.
Okay, I will just speak louder. Okay. So I just threw in the abort thing because it's going to be useful. But I want to give you the implementation for NQ, DQ, and first. Okay? So what is the implementation for NQ of some element E?
Can you try to put
So now the syntax for NQing is just an expression of my little lambda calculus. Sorry, of my little imperative language. Let's not name it lambda calculus. And it's the following. If I were to look at the valid bit, and I were to call the read method on it, you remember that there is a read method, and that this would tell me that it is valid. So I have the equal is one of those f, which is a pure combinational function. Then I would say, actually I can enqueue by writing the data, so data dot write of E. And I think there was slightly, oh, I said then else, okay, fine. Then, and then else, what do I do if I can't, there's already something in my queue, that is, there's already an element standing there, then I just abort, and that's a way to say the relation is partial in that case. Okay? So I can do NQ like this. Okay? And I can do DQ the same way. It's very easy. What do? I say if there was something valid, and dot read equal equals 1, then I say no, it's not valid anymore by calling the right method of the submodule, writing 0 to it. Otherwise, I am just saying nothing because I cannot deque from an empty Q, and I want the relation to be partial for that. Okay? And then what do I define first? Well, that's fairly straightforward too. If I want to read, and if you're telling me that there is something valid inside, then I would return simply the data that I stored. Did I write the data over there? Yes. Actually, there's a mistake here. Nobody got it. Ooh. What is the mistake?
Valid type.
Yes. Else, nothing. And so as someone pointed out, this doesn't work because I wrote the data, but I didn't write that there was a valid piece of data in this thing. Okay? And so I need to also write the valid. And then you're like, how can you both what is this new semicolon that you just added, and that, where is it coming from in the syntax of your language? And it's coming from there. Okay? Yes?
Wait, one more minor question. Does valid 1 signify an empty Q or a full Q?
Valid means that there is an element inside.
Because you said if valid is 1, then you added it on.
Did I cut the thing you want? It's possible. If, oh yeah, that's 0 here. If it's 0, then I can add you. And if it's 1, then I can deque. Thank you. Are we good? Yes.
I think there's also
Yes.
about the pitch of the valid axis 0.
Yes. Well, which case?
Sorry, I missed it. Sorry. Never mind.
There is no mistake. That's what you're saying. Yes. 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 So it's a very good. That's a very good question actually. Is a one element Q kind of useful? That's actually, I would have used that only one element Q are useful. Because the moment where you get more, then it costs a lot of space. And then you can't afford it. But it's much better to have a one element Q than to have just a vertister, because now you have this synchronization mechanism that guarantees that you cannot overwrite if the token has not been consumed. So, yes, very good question, and actually very useful. I think most design are mainly Qs and a little bit of things around. Okay? Any other question? Yes?
Is there going to be a type system for the language?
Yes, but it's going to be there, and when I'm going to program tomorrow, you will see it, but I'm not going to describe it, because I think it just adds loads, and it's good when you program, but when you describe it, it adds stuff. Good? Okay, so I want just to finish for 2 minutes to tell you why if you stay within these fragments, there is a very natural way to compile that thingy to hardware. And I don't want to describe you the compilation scheme that I might or might not describe you to you tomorrow, but I want to compile this specific example to hardware by hand and sort of like convince you by just saying it that, look, it should be generalizable. So the problem is that I don't know how much you know about hardware, but let's assume you know little. So at the bottom of hardware, what you always try to do is you have a bunch of states which are clocked by a clock, and you can think of hardware simply as being a bunch of registers, which are states, then a purely combinational function, which is a Boolean function that goes from state to state. So every cycle, you take a full set of Booleans in your world, you apply a pure combinational functions, and then you write a new value to the state. And you need to inject a little bit of input and a little bit of output. So where do you add input? You can say, well, actually, there is also input coming into that guy. And then you can also say, well, actually, here I can also fork off and produce some output. Okay? So fundamentally, a circuit is just a bunch of states, and then a network, in the sense of directed acyclic graph, of operator, which are pure combinational functions. And what are pure combinational functions? They are basically things that are generated by AND, or, not, and sort of the closure of those things, which is every single bootleg pointer. Okay? Does that make sense? Perfect. So, now in BlueSpec, the property that we always want to guarantee is the fact that the state element of the system in hardware is never going to be generated by some compiler. It's always exactly the state of the submodules that you have explicitly instantiated. So here, in my little example, I declared that I have two pieces of state, one valid and one data. So I can't add extra state. The only state that I will get will be one register for the valid. Oh, I need to draw. Valid. And one register for the data. Yes? And the question is, how should you update this whole thing based on NQ and DQ and first? And the super important trick is to say that you are going to represent the notion of method call by using a convention of signaling, where you're going to say every single method has basically three wires. There is one wire that tells you currently the method is ready to be executed, which is the relation is going to be not empty, that you can take a step. Then you're going to take another, so this is an outgoing wire where it's an output of the system. So here I'm describing the NQ case. You're going to get an enable signal, which tells you if the thing was ready, then as a parent, I can tell my kid do this that you told me you were ready to do. And data, which is the thing you want to enqueue. And every single method in BlueSpec is going to be encoded to a triple of ready, enable, and data. And in the case of every action method, and in the case of a value method, so you will have on the other side something for DQ, but you will have a ready and an enable. And then you will have also the first one, and for first you don't have an enable because it's not something that requires your module to know that there is no state taken, so you don't need to tell the module, please do something, it's just an observation. So you will just have a ready to tell you, actually you can do first, there is some value corresponding to the first method. Okay? And the question is, how are those wires connected to the wires corresponding to the ready read, with the data read, and the ready write, and the enable write of the internal registers. So the problem of compilation of BlueSpec is you have submodules with a bunch of ready and enable. In some situations, the ready is going to be hardwired to 1. And then you want to basically draw lines here, and then it connects there. Okay? And the question is, how do you draw the line? And in this situation, you can start by drawing the line one method at a time. Where you start by saying, well, you know, in hardware, I know to do if. If is basically a mux, right? So what I need to say is that sometimes I write to the data, sometimes I don't write to the data. Sometimes I write to the valid, and sometimes I don't write to the valid. So when do I write to the valid or when do I don't write, depend on the read of that thing, and of the fact that I asked to enqueue. So I'm going to look at the enable of the enqueue, and I'm going to say, if this is 1, so this is a control signal, that is going to come into some mux, and if, actually, if I'm going to control it, I'm going to say, when is it the case that I apply? So I look at the output of valid, which is the wire here. I compare it to 0. I get a signal. Then I end that with the fact that I indeed want to enqueue. And only when I want to enqueue and there was nothing valid, then I'm indeed going to enable the write of the valid. And then what do I write when, in the case where I write? Well, I write a 1 here. And then what data do I write where I have the data? This is messy. I will do that on slide tomorrow. It's going to be much easier. Okay? But I think that maybe I want to stop here instead of drawing more lines. The important takeaway for you is the interface is going to be represented by ready enabled. And the goal is to connect the internal already enabled to the external already enabled. And it's fairly easy to just consider every single program pass and then consider the mux of all the possible cases, and in which case you call which subset of methods. And if you call subset of method A, B, and C, which argument do you call to that method? And it happens to be the case that if you restrict the language enough, then you can normalize your term and know exactly what are all the possible cases, and there are finitely many of them, and then you can just generate out of work. Okay? Thank you.